Okay, great. So today we're going to have a practical walkthrough with FiftyOne. I'm going to show you a couple of things that I'm excited about. I'm going to tell you a lot about a model that is called Clip and how we use it inside FiftyOne for so many amazing things. We can use this for semantic search, deduplication, tagging images. And I'm also going to give you an overview about dataset curation and model introspection in FiftyOne. So I'm going to start introducing myself. I'm going to tell you a bit about what FiftyOne is, and then we're going to go deep into the topics. So I'm a computer scientist, and I work as an AI engineer and DevRel at Voxel FiftyOne. I'm also doing my PhD at the Hasselblatt Institute here in Germany. I live in Berlin. And I am an instructor at the NVIDIA Deep Learning Institute and also the Data Science Retreat. I like teaching machine learning. I like teaching computer vision, and that's also mostly what I do in FiftyOne. At Voxel FiftyOne, I teach the workshops about integrating FiftyOne with PyTorch. We have been doing a series of that during the last months. We're gonna continue this in a slightly different format in the next weeks. So as I told you, this is the agenda for today. We're going to be talking about FiftyOne as a tool for dataset curation and model introspection. I'm going to tell you a lot about image embeddings and a model that produces them that is called Clip that we use a lot inside FiftyOne. I'm going to show you how powerful it is, but I'm also going to tell you a bit about its downsides and the parts where it's not as ideal as a model that you fine-tune yourself. I'm going to show you also how you can fine-tune your own models with PyTorch and FiftyOne, and how you can use this to improve the quality of your datasets. So we're going to be taking a look at mistakenness, this metric for evaluating how wrong an object detection algorithm could be and also a classifier could be. And I'll show you how to integrate PyTorch and FiftyOne for training runs. This is a tutorial that I have been preparing for some time, and I'm gonna give you an overview of it. So first thing that I need to explain, what happens when you do pip install FiftyOne. FiftyOne is a Python package, so it has several things together. It has an SDK that we use to curate datasets. The dataset in FiftyOne exists in MongoDB, and it wraps together all of the annotations that you might have for your data alongside the metadata and the media files, which can be images, can be videos, can be anything that you encode as anything similar to an image or a video. You can put all your files if you put them into log mail spectrograms and things like this. So you can think of FiftyOne as a debugger and tracker for computer vision data. It allows us to do some slicing and dicing of the different ways in which we can interpret our dataset, considering all the metadata, considering all the labels, and everything that we might want to wrap together with the information that we're using to train our models. So FiftyOne has three parts. It has the SDK, which is this thing that I mentioned to you, this library that provides a huge amount of functions to work with the datasets that exist in MongoDB. We have the FiftyOne brain that it's mainly focused on embeddings, this concept that I'll be discussing today, and also some machine learning methods to assess things like mistakenness and hardness of samples when we use them for classification or object detection. And then we also have the FiftyOne app, which is a tool that we use to navigate datasets. It's very convenient. It beats by a wide margin having to navigate your datasets in your own hard drive or using this in Google Drive or using this anywhere else. It's a very cool tool that we can use to visualize the embeddings that we have for the data, that we can use to do aggregations on all the important metadata that we might have on our images or videos, and it's very complete. We'll show you today how you can load your own data into the FiftyOne app into the 51 SDK as well, and how you can do interesting manipulations on the data that you have put there. So the core concept of 51, as I mentioned, is the dataset. And a 51 dataset connects all metadata and annotations to media files. So all the tags that we might want to add to a particular image, for example, saying that it's mislabeled, or that a particular label inside the image might need to be revised or improved. These are things that you can add sample by sample. If you have a particular image, you can have a million tags. And these million tags, these million dimensions, are things that we can add iteratively as we're working on the data, either automatically or through visual inspection. We can have fields such as the embeddings that live alongside the sample. We can have descriptions in the metadata for everything that is happening inside any particular sample that we have in the dataset. It's kind of like a role in a structured database, or kind of like a row in an Excel sheet or a pandas data frame, but it's way more flexible because here we can put unstructured data. We only need to specify in an obligatory manner the file path to the media file that we're giving to the dataset, and all the other fields are optional. The IDs get automatically generated using a cryptographic hash so that they are unique. And then we have this flexibility that we can use to extend the analysis of our data any way that we want. So the dataset object is a container for the data that is composed of individual sample objects. And the sample is a data point, an image or a video clip. And this is, as I told you, the file path and any custom field that we might want to add. These custom fields can be whatever we might want to put there. This can be segmentation masks, this can be classification labels, this can be object detection bounding boxes. And 51 is very flexible in the sense that it's able to infer if a sample is an image, a video, or whatever, based on the file path. If I put an MPG file into 51, it's able to infer that this is a video file. The dataset is backed by MongoDB, and this is something that 51 manages mostly automatically. You can configure your MongoDB database, but you don't need to be an expert on MongoDB in order to use 51. This is something very flexible, and we are going to see how we can get this into basically any environment that has Python. You can run 51 in your Google Colab notebook, you can run it locally, you can run it on the cloud. This is something that respects the privacy of your data. If you put data into 51, this never goes to box of 51. This never goes to the company. This is your own private data, and nobody's ever able to access it externally. So we support all these different media types. We support DICOM files for medical images. We support point clouds, geolocation data. We support groups of data, so we can associate LiDAR point clouds with images. We support videos and images, as I mentioned. We can also use this to store information about key points. We can have everything that you might want to do with a discriminative machine learning workflow for computer vision, so classification, detection, segmentation, also regression, because you can store in your dataset things like the price of a car. That's something that I like to do in my workshops when I use 51 to store the predicted price of different cars. And this is something that is very easy to navigate. We can put relationships between different objects in the image. It's very flexible. So the 51 brain, as I mentioned, it's mostly the ML part of 51. It incorporates things like the embeddings, the manipulation of embeddings. I'm going to explain in a bit of detail how embeddings work. And we also use the 51 brain to do dimensionality reduction in order to visualize the embeddings and understand where do different data points are in this embedding space with respect to each other. When an embedding is good, things that are semantically and visually similar are close to each other. So it's just a point in space. I'm going to talk a bit about this. So the FiftyOne app incorporates tools to do visualization of the data and the embeddings. You can have all the annotations here separate from the original media files. So when you have bounding boxes on your images, it's not like they are drawn inside of the original images. They're completely separate. The app has this huge collection of utilities for us to navigate the dataset and the labels. We can, for example, take a look at bounding boxes and see which are the bounding boxes that would appear by different algorithms when we change the threshold for activation. So if I have a faster RCNN, like the one that is shown in this image, I can turn it on or off by just moving the threshold of confidence that we have for the bounding box. We're gonna see this when we work with object detection in the COCO 2017 dataset. I have an example for you guys prepared today where we're gonna be doing that. So using the app really beats exploring data the old-fashioned way. You don't need to navigate through the different directories that you have in your local computer and go into this very painful process of trying to figure out at which level did you nest the labels, or how do you associate a particular data frame that has the full annotation to the images. This is something that we do for you. FiftyOne has a very nice collection of dataset aggregation and navigation methods that allow us to work with the data in a very seamless manner. So for me, the FiftyOne really shines the most as a dataset curation tool. And it's able to filter, match, sort, and select samples. It's able to remove duplicates. It's able to remove extraneous metadata, things that you don't need. And it's also able to correct anything that you might want to change in your original annotations. So it's a great tool to wrap all these things together and actually make sense of the data that we have in a way that is disciplined and avoids making our workflows a mess. So it's a very good tool for ML ops workflows. And FiftyOne fits very naturally with ML ops workflows that are common in the industry and also academia. It integrates very nicely with PyTorch, with Spark. We have a very nice integration with Databricks that Daniel was presenting yesterday. It works very, very nicely with weights and biases, NumPy, scikit-learn. It's a native Python library, so you're going to be able to use it as naturally as if you were using scikit-learn or if you were using any library that is purely written in Python. And it has very nice integrations, especially on the enterprise side with the clouds. We not only have the free open source version, we also have an enterprise version that integrates with AWS, Google Cloud, Azure, so that you can put billions of data points into FiftyOne and have things like Kubernetes manage the scaling for your workflows. So there are two versions of the FiftyOne product. We have the one that is open source, and we also have the one that scales for massive data sets that might have billions of points. So FiftyOne supports all popular computer vision tasks, like I mentioned. It supports detection, classification, segmentation, key point estimation. It's able to group together LiDAR data with visual images. It's very, very flexible. And well, this is something that I think I mentioned already. We have FiftyOne as a linchpin for everything that you might want to do in your ML workflow that is interesting. So it's allow you to keep a good track of how the model training is going, like how are you interacting with your experiment tracking framework, like weights and biases. The data version control that we have on the enterprise version is a very powerful feature as well. So it's also amazing for benchmarking different models. That's something that I'm going to show you a bit of today. I'm going to be comparing a clip model that was trained on 400 million image text pairs with a very small model that was trained with only 60,000 images. And that's something that we can do very seamlessly in FiftyOne. So the open source version is great to use as a single user. It's great to use to visualize and curate data sets. It's great to use to find annotation mistakes, to evaluate and compare models, and also to find the root cause of poor performing metrics. Something that might be surprising for many people is that often things that we consider canonical in the machine learning community, like the COCO dataset, might have very surprising metrics when we evaluate them. When we evaluate a pre-trained model on their validation set, or when we want to deploy a model for which we know the mean average precision because it's what the people who wrote the model paper reported. And then we realize that the model is actually not as good as we expected. And then taking a deeper look at the data is the one thing that really shows why this model is not fulfilling expectations. We will find in many canonical datasets mislabeled data points. We'll find things that are labeled as a book that are a bookshelf, or we will find squiggles that are more spaghetti looking than number looking, labeled as numbers. That's something that I will show you today. And the enterprise version of FiftyOne, it's great for collaboration. So if you're working in a team of people where you're doing computer vision and you want to have a native integration with your cloud or your on-prem deployment, FiftyOne integrates very naturally with these environments. So it has out-of-the-box workflows that are also simpler to use than the versions that we have in the open source um, FiftyOne, and it has more of this governance aspect. You can give certain permissions to certain users so that only portions of the dataset are available to them. So it's a fully professional version of the software that you can use to collaborate with teams and to have clear compliance with access regulations that you might have at your company. So I'm going to start here describing the problem that we're going to be doing today. I particularly like to collect images from Google Earth. Google Earth View is this collection of images from Google Earth that is actually quite nice to look at. And I often download images from it. Work a bit on, sorry, I'm gonna answer your question later. I work a bit on uh, image analysis of multispectral satellite images a couple of years ago. And ever since I got hooked on this particular topic. And this is something that, I just like to look at. Sometimes I save these images into my hard drive, and then I do some collections or analysis based on what I have here. I like using these images for teaching because they're beautiful to look at, and they have several challenges. They're like very high resolution, so one needs to think about how to pre-process them to get the best quality possible out of a segmentation or out of a classification or even a similarity matching. So let me take a look at the questions. Are we having the Zoom? Somebody was raising their hand. I'm not sure if I can see this. Would you like to write your question, Anusha, please? Please write it on the channel. So, okay. I like to download these images. I put them on my Google Drive or I put them into my local hard drive. And sometimes I make mistakes. Sometimes I download the same image twice, or I do a mistake in the naming of the image, or sometimes I just care about a particular area of the image and I just take a crop. So I just save a random crop of the image. So this creates problems for me when I want to do machine learning with these images. I need to know if this collection is duplicated or not in order for me to be with some trust in the model that I'm training. If I train a model with duplicated images and then I have duplicates between testing and validation and training, then the metrics that I'm reporting, the classification, the precision, the recall are bullshit. They're not true. They're inflated because it's as if I am cheating while I'm training the model. So this is something very important to do when we're creating supervised learning models. We want to keep the dataset as free of duplicates as possible. And that's a very important pre-processing step. That's something that we as practitioners need to be very careful about. And here, I'm going to show you a workflow about how to do this using embeddings from a pre-trained model. We're going to be using Clip, which is amazing for several reasons. It's probably not the best model to deduplicate aerial images, at least the version that I'm using, but it's good enough for us to get something that is quite interesting. So when I curate this data set, I want to know which of the images that I put into my 51 dataset are the ones that have higher resolution. I want to label them as well as possible, with as little effort as possible because I'm a lazy person. So I don't want to spend hours labeling these images. I want to do this in a way that scales. And I want to be able to find similar images in my dataset. I also want to be able to find which are the most representative samples so that when I create my machine learning model, I can do quick experiments and then I can get quick benchmarks by evaluating the representative images that I have in my dataset. So I'm going to give you a quick intro about vector embeddings. Dense vector embeddings are one of the most amazing things that we can produce with a neural network. Whenever we put a data point into a fully connected layer, we produce a dense vector embedding. And what I mean with dense is that it has values in almost every position of the vector. This is different from the embeddings that we use to encode the labels, which tend to be sparse. For example, if I want to use a vector to represent the labels for this digit 3, I'm going to be using the position that corresponds to that, to one hot encode that label. But if I want to represent these two images as something that makes sense for the neural network, I should put them as 2 points in a very high dimensional space where they're close to each other because they belong to the same semantic class and they look similar. They're threes. So we use metrics to compare embeddings that are basically the same that you would use to compare any 2 points in space. You can use the Euclidean distance or the cosine similarity to compare embeddings. And this is because it's just a point. It's something that lives in a very high dimensional space, but it's just a point. And when we train the model well, then these two embeddings, these 2 points are going to be close to each other. And we're going to be able to do interesting operations on this. So for example, the duplicates are going to have almost the exact same embedding. And images that are semantically similar are going to be close to each other. So this is a visualization of embeddings projected in a 2-dimensional space. Well, you could say that it's 3-dimensional if you include the color, because you were also looking at the uniqueness of the embeddings. And here we have the images in the dataset And you see that I'm going to show you this. You're going to be able to play with this in the code. You're going to be able to select different point clouds in this embedding space. And when they're close to each other, these point clouds, they're going to represent images that are similar to each other. We project the embeddings that are in a very high dimensional space, like 512 dimensions, into 2 dimensions in order to do these explorations in a way that is easy. So this is a slide that I stole from Paula. I really love it from her presentation. When we embed a dataset, we're really able to see it clearly for the first time. When we put it somewhere in this space and the network has been trained correctly, then we can do many, many interesting things, both by fine-tuning the embeddings, both by manipulating the embeddings, and also by using this as input features for other machine learning models. So it's very powerful. And I think that embeddings are like the true magic of neural networks. Being able to put these unstructured data sets that have such a high dimensionality into a space where they're easier to manipulate and think about is the true power of neural networks. It's as if they're compressors. They compress the embeddings in a neural network. The embeddings that are produced by the neural network compress a lot of the semantic and visual information that we have on our images. So here you see an example. Here you see the different digits of the MNIST dataset that we're going to be playing with. And you see how after we have trained a good neural network, and this is a LeNet. This is a network that was specifically designed to be good at this particular dataset. And we embed the vectors that we get out of it in 2 dimensions, and then we plot them. We see that the different digit classes correspond to a different area in this space, with some exceptions. The digits that are a 4 that kind of look like a 9, or the 3s that look like a 5 are going to be the anomalies. And we're going to be able to use things like this distance from the cluster centers to say whether a particular data point is representative or not, and how likely is for a particular data point to be an outlier for its class. So we're going to be using this particular model, CLIP. It's an amazing model from OpenAI, possibly my favorite thing from the last 10 years. It's a very powerful model that it's not only able to embed images, it's also able to embed text. And when we do this, we're going to be able to do things that are quite interesting. We're going to be able to do semantic search within FiftyOne by leveraging the power of CLIP, by putting some query text into a text embedding and then an image embedding into the embedding space that it's forced to be together during the training of CLIP. We're going to be able to retrieve images that are similar to what we ask about. So if I write a query asking for a coast, I'm going to be able to get images of coasts. So this is the thing that we're going to be doing. This is where we start with the hands-on part. Here you're free to follow along if you want, but the notebooks are already shared with you. The links are on the slides. You only need to click there, and if you find an issue with any of them, please let me know. Something that I will invite you to do is to join the Discord community that we have for FiftyOne. I have a channel called Practical Computer Vision there, where I answer all the questions that you might have about the content that we present to you in these workshops. So if you have a question about what's happening in the notebooks while you're working through them, please feel free to write a question in the Discord channel. So this particular notebook, you're going to be able to find here in my repository called Practical Computer Vision. And here we're going to be doing this evaluation. First, we're going to start looking at the metadata for CLIP. Sorry, the metadata for the dataset that we have. We're going to be loading the dataset into FiftyOne. We're going to be evaluating what is the distribution of the images in terms of size in bytes. Some images are very big, some images are small. And this is where we're gonna be starting. I'm gonna go now into my Visual Studio Code, and I'm gonna start running this notebook to show you how to play with this. So in the repository, you're gonna find a requirements.txt file where you have everything that you need to run these notebooks. You're gonna have to install FiftyOne 1.5.2. This is what I use to test my notebook. And you're gonna need to install Torch. Also augmentations for things that we're gonna be doing later. But please try to do this with a virtual environment. Please create a virtual environment with Venv before you do this. Don't trash your computer, don't trash your Python environment. There are instructions about doing this in the repository. If you go to the repository, you will find a setup guide where you will see how to do the installation of FiftyOne with Venv. You can find this here, Private Computer Vision. You'll find here this guide about installing FiftyOne with Venv for local development, which is exactly what I'm doing today. I'm using FiftyOne locally. So, okay, here is my notebook, and I'm gonna start doing the imports, and I'm gonna start getting my data. I have 153 images in this folder, and now I'm gonna create the dataset. This is how we create the FiftyOne dataset when we have a folder of images. I'm gonna specify that the type of this folder, the type of this image folder is an image directory. So here I'm gonna let this run very quick. And now I'm gonna compute the metadata for my samples. And this is something that I want to do. I also want to add the metadata of the number of pixels that I have on every individual image, not only the height and the width. I also want to include the metadata for this. And after I have done this, I can launch the app. Notice that I put this with auto false. This is the way that I prefer to do this in my notebooks so that I can open FiftyOne in a full-size window. And here we see all the images that we have in the dataset. If I want to start doing aggregations here, for example, to check what's the distribution of image sizes, I can go here to histogram. I can put this side by side. And here I can do things like, well, let me do size of bytes, which is the first thing that I showed you. Here you see that we have kind of a bimodal distribution. Like here we have, I can also visualize this here. Some images that are very heavy, and this one that is lighter, almost half the size in memory. If I want to do here, for example, let's see how the width looks like. The width is even more bimodal. We only have basically two types of width. And I can also take a look at the height. And let's see, did I put, it's okay with this. Here I'm gonna start using the clip model. So FiftyOne has a zoo of models that we can use. This is gonna be a clip based on a vision transformer implemented on PyTorch. And I'm gonna be saving the embeddings that I get from this model into a field for every single sample. And I'm also gonna create an image index. With this image index, we're gonna be able to do things that are very interesting because this particular model supports prompts. And check it out here. You can see that we have 152 images. Each one now has a 512 embedding. And I can, Let me see if I did refresh. Did I do refresh? I think just need to do the session view, dataset view. And now I can do things like sort by text similarity. Should refresh this. Here I can type anything. Let's say that I want to have my aerial image, a coast. So what this is gonna do is that it's gonna embed this text query, and then it's gonna retrieve the most similar images, the ones that match this description. These are aerial images that look like a coast. It's kind of like having a Google image search for our data. Here I can do things like I want to search now for an aerial image of an airport. And let's see, these are some park airplanes. This is close, not really an airport. These are railway tracks. This is a stadium. Here we have an airport. So you can see that this allows us to navigate the dataset in a way that minimizes visual inspection. It's not that the description is perfect or that the embedding is perfect. There are going to be things that don't match fully, but this is already a huge win versus doing this by navigating the folders of my Mac OS. So this is very convenient. Let's try one more query. Say that I want now, let me reset this, refresh 51 here. And what could we put? Let's see. Export an aerial image of ships in the ocean. And here we have these three images, also these containers, and also images of the ocean. So not that bad, right? Here, we're going to be doing the dimensionality reduction in order to visualize the embeddings in a two-dimensional space. And after doing this, I'm going to have to refresh the session so that the 51 app is in sync with the SDK. Here, I should be able to have the embeddings already. I did compute visualization, I did. So just need to refresh. Now we have the brain key for the principal component analysis that we did. And we can see this side by side. As I told you before, if I select a portion of points in this point cloud, this should represent images that are similar to each other, both semantically and visually. So let's check it out over here. Let's check it out over here. How about this particular image here and this too? Let's see. This one is not being picked. There's something weird in this embedding here. Let's check out this section here. I can also color this by any of the fields that I have here. We computed the uniqueness, which is in light color for images that are in a cluster that is less dense. So what we do is that we run a clustering algorithm and we find which are the images that are in the less dense clusters. These are the most unique images. Let's see what we have over here. Let's see what we have over here. And let's see what we have over here. So you see here that we have a duplicate. And this duplicate was embedded twice in the same space because it's the same image. It's an exact duplicate. It has the exact dimension in the number of bytes. I'm going to show you how we can detect these exact duplicates. It's a bit different than detecting the approximate duplicates. For exact duplication, we use cryptographic hashes, and we have some very nice utility in FiftyOne that tells us when two images are exactly the same, not approximate matches. So let's see what else we can show you. So you can also do this sorting. Suppose that I want to get rid of this now. I don't want this stage. Suppose that I want to sort all of my images by uniqueness in descending order. And look what happens. The images that are duplicated are going to have low uniqueness naturally. So this is going to be the first position, second position, third position, fourth position. These are all redundant images. These are very similar, so they appear next to each other. This is what we get when we sort the samples by uniqueness. So let's check out this functionality of computing near duplicates, which is something quite powerful in the FiftyOne brain. Here I'm gonna get from this simple call a view, a FiftyOne view that shows me images that are near duplicates. So this pair is near duplicated, this pair is near duplicated, again. So I'm gonna have to select one of these images to keep, and I wrote my own logic for doing that. I'm sure that I could have done this easier with the neighborhoods from the FiftyOne index that we have here, but I already had this code. I had already created my own logic for doing this, the duplicator. So I wanted to try it. So I have here a couple of things that I did just for fun. I wanted to get my embedding separately. I wanted to compute the similarity matrix between every single embedding and all the others for all the images. Then I wanted to get rid of the self-similarity in the main diagonal. And here I have some statistics about what's the mean similarity between two data points and what is the standard deviation of similarity. I want to take a look at this to decide which is the threshold that I'm going to be using to deduplicate my images. There is no hard rule for this. I cannot tell you that you should always duplicate your images when you have similarity above 0.8 or above 0.9 or 75. You need to take a look at the distribution in your data and see if it makes sense to you. It's trial and error. So here I have this exploration just to figure out which could be the thresholds that I use to deduplicate my dataset. And I also wanted to have an idea about what's the max similarity between any two samples that I might have. So here we have all this computation. You see that this is all scikit-learn code that integrates very naturally with FiftyOne. You see that here we have this enumeration of the dataset where I'm getting the indices of the values and also the particular samples that I have in the dataset, the different rows, by just writing a simple loop. So it's very natural for Python programmers to gain familiarity with FiftyOne. The learning curve is not steep at all. And here I have this visualization of my dataset by images according to their max similarity and which is the pair on which they had max similarity with. So you see that I can have this here, and here I have these two images, and one is most similar to the other. I can check out these fields here by taking a look at the ID of every single image. And yeah, this is how I can navigate the dataset with PyTorch code and a bit of experimentation in FiftyOne. So here are the duplicates that we have identified, and I have decided that I want to keep the larger image. I want to keep the image that has higher resolution. And sometimes the images might be in JPEG, sometimes they might be in PNG, so I cannot use size of bytes for that. I need to use the product of the height and the width. So I wrote some logic for doing that and for tagging the images for removal based on the similarity threshold and the image size. So here I'm gonna evaluate this. And after running this deduplicator, I get rid of about half of the images. And if I evaluate my view again, I'm gonna be able to see which are the images that are labeled as keep or remove. Let's say these are the images that I'm gonna keep. These are the larger images. I tag them in FiftyOne to keep some consistency in my dataset to actually also track later which were the images that I chose to keep. Maybe I change my mind later. I want to be able to change my mind, and I want to be able to track every little change that I did to the data. So you can see here, these are the images that I want to remove. Most of them are crops of bigger images. And you can also visualize this like this. Finally, I want to export the dataset because I want to use this for the next stage of my workflow, which is to label the images. I'm going to be using the clip model to label my images, but I'm not going to use only one clip model. I'm going to be using 5 different variants of the clip model, and I'm going to decide which of this I'm going to keep, either by the one that has the most confidence or the one that is just the aggregation of all the different values. And here I think that I made a mistake because when I export the directory, yeah, there is a mistake here because I'm exporting 152 samples. So I'm not exporting the deduplicated version of the dataset. There is something that is wrong in my logic here. I'll figure this out and I push the new version of the notebook to the repository. Anyway, let's move to the other stage. There's not going to be much of a difference in the result here because we're not actually training this model. We're just using this for inference. If I had been using a training pipeline here, this would have been critical. Like this mistake that I did in saving the wrong version of the data would have really like trashed everything that I would have done later because the metrics of precision, accuracy, and recall would have been completely false. So let me show you what's the idea here. I'm gonna select my virtual environment. I'm gonna get my images again. And let's just create a dataset again. I don't have a GPU on this computer. This is a MacBook, but it's gonna be good enough for me to run clip with all these different prompts. I took a look at the images and then I decided what could be the best prompt that I try on them. This is a river in the jungle, a river next to an urban area, a river delta merging with the sea. I don't know if you can read this clearly. Maybe I should make my font a bit bigger. You actually see this thing here. And here again, I'm just gonna load the same model. And I'm gonna be running this, but now for classification. Let's see what's happening here. Label field, zero shot classification. I think there is a mistake here because I think I'm importing something that is completely empty. I think it's because I changed one of the paths here. So here, let's see. What did I do wrong? Save OS list here, aerial images, path. I think I changed, yes, I changed the path of some folder here when I was doing, yeah, when I was working on the repository. There is something broken in my paths here. I think I'm just gonna show you the illustration of the idea here because it's, I think it's already in the version that we have here on, let's see, I think I actually have this running on Colab. I think I can show you the Colab version. Google Colab, yeah, let's see. So what you see here is an image that has been labeled 5 times by 5 different models. These are 5 different clip models, each one given a confidence for its interpretation of the image. A coast showing the near-infrared channels, vegetation on water bodies in the near-infrared channel, vegetation on water bodies in the near-infrared channel, like all of these things, each one has a confidence. So what I'm gonna do is that I'm gonna take the majority vote of these different labels, and that's gonna be the label that I'm gonna apply to my images so that I can have some label images without me needing to train any model. So I'm gonna do now is that I'm gonna run everything here and pray to God that this particular version works. I think this is not gonna work because I forgot to fix this path here. Sorry about this. Here, this is fully my fault. Put here 351, it got 1.5.2. And this one should be dev null, so it doesn't print. Did install 51. And here I'm gonna have to mount the Google Drive folder. So let me show you quickly how to do this. I'm gonna go here into mount from Google Drive, mounting Google Drive in your VM. I'm gonna be opening the file from Google Drive. I'm gonna insert this. I'm gonna run this here. And I'm gonna start defining some paths as soon as this finishes running. I have the images on my drive, and we're gonna be able to run this from here. So here I have aerial images, and this is the path that I need to give to my Google Drive, sorry, to my Google Colab instance. So let's see, we have here the duplicated images. This one is empty. This is, okay, let's do this one. Aerial images without what? It's gonna be aerial images without duplicates. So I'm gonna define this. I'm gonna say that I'm gonna allow this to happen. I'm gonna allow this to connect to my Google Drive. I share this folder with you on the notebooks. You can also download it, or you can follow the instructions on my repository so that you can copy the path to your own Google Drive without having to download anything. That's actually much faster. And I have instructions that you can follow for doing that in my repository. Let me just share this with you real quick. We go to Practical Computer Vision. We have this section here, dev container, this one, copying data folders without download through Google Drive. So this is something that you can try to run my code. Actually, just give this to you. Put this on the chat window. This is how you can get my data. And look what I'm gonna do. I'm gonna define this path here. I'm gonna say that I'm gonna have here from pathlib import path. I need to adapt this from, instead of using my local folder, I'm gonna have to use the folder that I have in Google Drive. That's the one change that I need to do. Let's do this real quick. Let's put here path is gonna be G drive, then my drive, then the name of the folder, which is, let's see here, it was, trying to fix this. This was in aerial images. Get here, 51 getting started datasets, and then aerial images. It's gonna be 51 getting started datasets, then aerial images, aerial minus images, and then aerial underscore images underscore without duplicates. Aerial underscore images underscore without duplicates. And let's see if the gods smile to me now. It's gonna be path for this. And to check that I have the content here, I'm just gonna write OS this dear path. Doing inside data sets, aerial images. Okay, yes, here we have the data. I think the one that I need to give is actually data here. Yeah, so these are my images. I'm gonna hide the output. I'm gonna put this as aerial images path. Let's call this, let's delete this. And let's call this aerial images path is equal to the path that we just defined. We have computed the metadata. I did something, let's say, change runtime type. I forgot to put the GPU here. Let's just put this real quick. And now we're gonna have to reevaluate this, but other than that, should be okay. Just gonna delete this section here. And I'm gonna run everything. So whenever we create a new Colab instance, or whenever we attach a GPU, we need to reinstall 51. This is a reason why I mostly prefer to do my experiments in the local machine, because here we lose the environment. Like, this is something that is reset now. We have gotten now a new machine, and now we need to install 51 again. We're also gonna have to connect to Google Drive again. But I think it's gonna be okay. I think this should be completely fine after this finishes running. Gonna connect to Google Drive. Continue. Continue. Gonna run this. It's the path. Aerial images tag. Let me see if there are some questions that I can answer in the Q&A while we let this run. Exact match. Features. We have 6 answered questions. Okay. Let's see. Here we have the text prompt and aerial photo of. The results that you get out of clip are actually sensitive to this text prompt. If you just write a photo of instead of an aerial photo, you're gonna get a different probability for the output. So this text prompt is concatenated to every single prompt that we have here in the classes. So it appears as the prefix of every particular class that you might have. And let's see, we're gonna have the model. We need to download it again because this is a new environment. This is not the thing that we had locally. And now the model is loaded on the GPU. Whenever we have this message saying that the model is already on CUDA, that means that the model has been loaded on the GPU. I'm gonna go here into non-cell and below. And let's check out what's gonna happen here. And I think that something that is missing here is the pip install of OpenClip as well. So it should be pip install OpenClip torch. Let's check out if this is the correct install. Yeah. So this one has already computed the predictions using one single clip model, but I want to get 4 more. So for that, I'm gonna be using OpenClip. Here I get the prediction from the original clip model from OpenAI in the base version, which is not the biggest one, not the most powerful, but it's very useful. Like we saw it already for semantic search. And here you see the labels that the model is assigning to the images. So this one is labeled as a body of water next to an urban area. And I can take a look at the confidence that we have on this. This has a confidence of about 0.37. Let's check out what we have here. This is actually a mislabel. This is not the Antarctica or Arctic water. This one is way more difficult to label. This is a desalinization plant. I didn't include this in the possible labels, but it's understandable that the model had trouble here. You see here, this is a farmland, a desert next to a body of water. This is actually a full body of water, and this is an oil rig. So this was not captured correctly. Here we have a beach next to an urban area with this particular confidence, which is very nice. Let's see what we get when we run the other clip models. Here I have clip A, I have this data filtering network, EVA2 clip, and MetaClip. And now let's see if we can run this. This is going to be relatively quick because we have a GPU. And here I'm going to say that I'm going to grant access. I have my Hugging Face token enabled on my Colab. So let's see. It's going to take just a couple of minutes. And let's see what we get out of this ensemble of models. What is going to be the prediction that they agree on? I included some logic to aggregate their labels. And this is what we have here. We have the labels and the confidences that we have on these labels. What we do is that we take the most common label out of the 5 evaluations, and then we take the mean of those matching labels as the one confidence that we're going to get out of this ensemble of models. So let's see. These models are still downloading. OpenClip is being downloaded from the PyTorch repository, 600 megabytes. It's a big model. Let's see what we get out of this. Did this finish running? I think it did. Let's see. Close here. So here we have the different labels that the 5 models are giving. And you see that each one of them has a confidence margin. I can actually filter the samples where one of the clip models has the most confidence. You see, like here, these tend to be the images that are better labeled. So here we have containers in a harbor. Very well. This one like all the models agree that these are containers in a harbor. This one, some models believe that it's a river delta merging in the sea, which is incorrect. There is no sea here. And two of the models believe that this is a river in the jungle. It's important to know that this is not a model that has been fine-tuned for satellite image data. There are variants of CLIP that are specifically for satellite imaging data. This is just a general purpose CLIP that you can use to tag images of dogs and cats or whatever you want. And let's see what's going to be the output of the aggregation. So here you can see that we can inspect the samples, and each one of them have the label predicted attached and also a confidence for the label alongside the logits. And let's see what are we gonna get here as the most common label. Let me run this. This is the session after being refreshed. And let's turn off all of this and just keep the most common label. We can have also the full spectrum of confidences here. You see, we have a river delta merging with a sea, a desert next to an urban area. This is nice. Antarctica or the Arctic area, ice and water. A beach next to an urban area, like all of these things. Well, this one is one where the models are having trouble. A farmland, farming terraces. In this particular image, the one where the models are having trouble, I can save this. You see that this one, I can add a tag. I can tag that particular image and say that I would like to inspect this further later. So this one is also wrong. River delta on the sea. I could apply some label tags here to filter this out later. Colab is also a bit slow when accessing the data from Google Drive. That's why we see this bit of a lag that we did not see when we were running the app locally. Here you have this. We can apply a label tag, say that I want to tag this image. And I'm going to say that this is not the sea. And that this is something that I can refer to later so that I remember to fine tune this particular data sample and the others I keep. So this is a process that is iterative, and I have reduced a lot of the manual labeling that we need to do on my dataset by using the clip models. So they are an amazing tool for dataset curation, and even better when you use the specialized variants of these models. Here I use the general purpose clip. I didn't use the clip model that has been fine-tuned for satellite images, which will be even more confident and more precise for these particular labels. So that's what I have to show you on this particular section. I can share this notebook with you guys with these changes so that you can play with it. And if you have questions about it, you can ask through the Discord channel. So let's continue with the presentation. Let's see, I have my slides. We already did part 1 and part 2. Next thing that we're gonna be doing, it's continue playing with the embeddings, and we're gonna continue playing also with Clip, but in a completely different setting. We're gonna be using a different dataset. We're gonna be using the MNIST dataset, which is this thing that is kind of like the hello world of computer vision. This is something that everybody who has coded a neural network for vision has done at some point in their lives. And we're gonna see that we're gonna be able to find errors in this dataset. It's surprising that even though it's something that everybody is using to learn computer vision, it still has errors. It still has some digits that are malformed. And in Kaggle, you will see many discussions about what people do to achieve a perfect accuracy in MNIST. And it turns out that with the dirty data, the noisy data that we have in MNIST, it's impossible to achieve a perfect accuracy. You actually need to cheat. You actually need to put the images in the test set in the training to actually create a perfect classifier, because there is corrupted data inside MNIST that impedes creating a perfect classifier. You're gonna have like O's that have like a little hat, or numbers that look like spaghetti but are labeled like 6, and things like this we're gonna be able to identify with 51 and a fine-tuned model for classification. So we're gonna be taking a look at that after we do a brief exploration on embeddings. So this is where I'm going to be ranting about how you can out-train bad data. This is something that we're very convinced about at 51. We're a dataset curation and model introspection platform. So we believe that you cannot create good models with bad data. And this is something that has very serious consequences in terms of bias, systemic errors. The performance of the model is going to be poor if you feed it garbage. Garbage in becomes garbage out. This is unavoidable. And here we have a collection of articles that you can take a look at. You can Google this and you'll find many, many concerning stories caused by poor data quality. And here we're going to take a critical look at one of the most common datasets for computer vision, which is the COCO 2017 validation set. We're going to be evaluating how well are the books labeled in the COCO 2017 validation set. Take a look at this. What are the iffy things that you find in this particular data point? You see that we have a bookshelf labeled as a book. Then we have this individual books. Several of them are labeled, but most of them are not. And then we have like these big chunks that correspond to several books also being labeled as a single book. This is an issue that many researchers have reported with the COCO 2017 dataset. This was crowdsourced to human annotators, and there were like some iffy guidelines for many of the classes. People are easy to tag on this dataset. Cars are easy to tag on the dataset, but small objects, things like books, plants, sometimes have some very poor quality masks. And we're gonna be taking a look at how to create a dataset that only focuses on the books first, the images that have books from the COCO 2017 validation dataset. There's only gonna be like 200 of them. And then we're gonna be taking a look at the mistakenness metric that we can use in 51 to address the annotation errors that we have in this particular example. So let's go back to the VS Code. And let's take a look at what we have here. This is going to be the first notebook. We're going to be creating and saving datasets from the 51 app. So I'm gonna again choose my virtual environment. I have here a list of downloaded datasets already on my computer. The COCO 2017 dataset I fully downloaded first. And here I have this, let me just load the dataset. And let's see. So these are the full 5,000 samples. I don't want to get all of them. I just want to get the images of the books. And I want to show you how you can do this through the app in a way that is very easy. Is very simple to filter samples by a particular lab, by a particular tag or a particular label through the app. Here I can go filter by label. And let's say that I only want the books. I'm gonna get here, book. And what I'm gonna do now is that I'm gonna save this view. A view is, well, I already have it here. It has already been saved. Let me actually delete it so that you can see how I create it. I can go here, again, ground truth. I'm gonna filter by label, book. And let's say save current filters as book. Let's say here, this is gonna be like my new books view. I'm gonna assign a color here to this. Say that this is gonna be purple to make it distinct to the other one. And whenever I want to reload this, I just click here. You see that these are the books already filtered in the dataset. Every image that we have in this particular uh, collection has a book in the ground truth. These are questionable books. These are not the best labels possible for books, but this is what we need to sample to actually evaluate the quality of this labeling. So we see this one here. I think I have a session of 51 already open. This is why I'm getting this flickering. Let me just close this here. Yeah, I have 2 sessions of 51 open. So here we have it. So take a look at this. This is terrible. I would like to get rid of this particular tag. I would like to say that this is a bookshelf. I'm gonna say that this is a bookshelf, not a book. And this is a chunk of slanted books as well. I'm gonna label this as well. I'm gonna say this is a chunk of slanted books. Like these are things that I don't want to label as individual books in my dataset. And you'll see that there are many more of this. Here I have also this huge chunk, you see? Like all this thing here is labeled as a book. This is terrible. Like the model is gonna learn to associate like a big shelf or a big chunk of a shelf with the label book. It has no deep semantic understanding. If you give it this as the label of book, it's gonna believe that this is a book. So again, we're gonna put some labels here. We're gonna say this is chunk of books, something like that. And we can retrieve this later. And let me show you how do I export this into my VS Code. I want to create a new dataset from this. I want to take this view and take all the samples from it. Here I have, if I go to list saved views, you see that both of the views that I created through the app are available through the SDK. So here I can load the original books view that contains 230 samples. And I can say that I want to store this in my local hard drive. That's what I'm gonna do. I'm gonna store these 230 images by doing export media true and override true. So these 230 images are now stored in my hard drive. And I can use this for the next stage of my analysis. What I'm gonna do, I'm gonna try to run a pre-trained object detector to produce some new candidate labels for these images. And let's see if the model is better than the data. Here, I'm gonna be importing the data set. Here I have imported the data set that I filtered, these 230 images. I have said that the field that we're gonna be using for the labels is ground truth. Again, I'm just gonna compute the metadata for sanity's sake. And here I'm gonna launch the app. And let's see. Here we have exactly the same thing as before. It's still flickering because I have this open twice. And by the way, you can have multiple instances of the 51 app running if you just specify different ports to avoid this flickering thing that I have. When you have like 2 instances running, you just need to define a different port by default, we have 5151 as the port. You can put here launch app, and you can say that this goes to port equal 5252, for example. And then you can have two views of the data that are completely independent of the other. So now I can launch this again, and then I'm gonna have this in a different window without me having some flickering with the other values. Wait, why is it getting some flickering? I don't know. Okay, so let's see what I have here. I have the faster RCNN model. This is something that I got from the 51 model suite. And I'm gonna be running this in batches. Actually, this one says it doesn't support batches. I made a mistake here. I should have chosen a model with batches. What this faster RCNN is gonna be doing is gonna be producing bounding boxes for all the pre-trained labels in COCO. In COCO, we have about 90 different classes, and one of those is books. You see, this is the validation set, so it has the same classes that we have in the training data. And what I want to see is how good are these predictions versus the ground truth. Like we have some ground truth that is very noisy, is very bad. Maybe we can identify that there is some mistakenness in this labeling. Maybe we can identify that the data points are missing here, and we can do this with help from a pre-trained model. In 51 Enterprise, we have a new service that is called Verified Auto Labeling, that it's basically doing this at scale with a huge collection of foundation models that already know how to classify and segment and detect the bounding boxes of images. So this is a good way for us to save effort in labeling using pre-trained models that already know a lot about the world and doing aggregations of them, just like we did with the clip model, like we did before for the labeling of the aerial images, is a good way to get signal for our labels. This reduces a lot, by 10 orders of magnitude or more, the effort that you will need to put into label these images by hand. So this is something that has become a trend in recent years. We are going into this data-centric development of AI, and it's where I think most of the value comes from actually curating very high quality data sets that are representative and that allow us to have a good understanding of what would be the situations that the models are facing in production. So when we have a good training and validation and testing data set that is similar to what the model is facing in production, we're able to create models that are robust and that are actually reliable. So this is a screenshot of the output of mask RCNN for this particular sample. And we see that it has gotten way more images. It's still, however, not perfect. And we're gonna take a look at that. So let's take a look at what we have here. Close this. And let's take a closer look at this particular image. So first thing that I'm gonna do is that I'm only gonna get the filter by label book because I don't want to get the other bounding boxes. I have this here. And now I don't want to see the ground truth detections. I already know that they are bad. I want to take a closer look at the predictions from this faster RCNN model. Let's take a look at the predictions with low confidence. Let's see. Even they are low confidence. Let's see what we have here. This one is pretty good. Maybe just putting two books together as one. This one is putting one book together, only one book. This one is miss at this level of confidence. Let's see what happens if we make the threshold a bit bigger. You see that there are some labels here that are still bad. Like we're still labeling like this whole chunk of books as one singular book. This is undesirable. We don't want to have this. And we can also change this label. Every label that we have in 51 has an ID. It's like an object on which we can aggregate more annotations. So here I can say that this particular label, like this is actually not good. So here, let me just close this and let me get rid of this. Maybe I should put like some clicking a lot where I shouldn't. Just get rid of this. And let's say that this particular label, we have already 3 selected labels here. We have also this one and this one. So this one is also something to get rid of. So this is chunk of books, something that I can keep in mind later. This reduces a lot of the annotation effort of cleaning this particular data set. You see here that we also have some false positives. This is not a book at all. And you can imagine that these issues exist not only in the validation data, but also in the training data. So ideally, we do this thing over and over. We curate the validation data, we curate the training data, and then we retrain the model. We fine tune it so that it stops picking up these false positives. And you see that the crazy thing is that this is a model. This is a data set that we're using to benchmark the models. When you go to the website of the creator of YOLO, for example, you will see that he's benchmarking his results against the COCO dataset. And we see these metrics that aggregate the mean average precision for the dataset based on all the different classes that you have in COCO, even though some of them are very dirty, some of them are very noisy. So there's a lot of work into improving these data quality issues. And I included in the notebook a discussion on one particular paper that I like. It's called COCO-Rem. Here they're using an approach that is very similar to what we're doing with verified auto-labeling to clean the COCO dataset. So if you want to use a COCO variant to fine-tune your models, I will recommend you to go into this, to actually use the COCO-Rem variant instead of using the original COCO dataset when you want to assess the quality of your own object detection or segmentation models. So that's all that I have to show you for this section on object detection. We're gonna have, do we still have time? Yeah, we still have time. We still have time to go into, but wait, I forgot to mention something that is important, which is the mistakenness metric. Here it is. So 51 Brain has this compute mistakenness function that we can use to compare the output of the predictions from faster RCNN or any particular model with the ground truth. And we're going to be able to get some very interesting signal out of this. Let me actually run everything here. Let's see. Something that is missing in my data set. Let's go from here to here. Oh, wait. What did I do? Did I do apply model? No. Stop this. And let's go from here to here. Let's see. Label field. I think it's because I saved this one. It's detections. Why does it have, there is something that is missing in my example here. Sorry for my mistakes. I have something that is off in my import here. Let's see if I can get this. Label field should be ground truth. This corresponds to the ground truth labels. Faster RCNN prediction should already be there. Let's check out the schema that we have here. Let's say we have a sample, right? Equal dataset first, a sample dot get field schema. Let's see, it's called ground truth detections. So here label field should be ground truth detections. And now, oh God, I reloaded, so I will have to let this run again to get the mistakenness. So here, yeah, I reloaded the dataset, so I didn't allow it to, yeah. So let's go here from, yeah, we'll need to rerun this evaluation to get the predictions again so that we can get a mistakenness. Sorry for my messiness today. I have, while this is running, I have the chance to start explaining to you the next example, which is the one where we're going to be using two different models to try to evaluate the quality of the labels of the MNIST dataset. So that's something that I have in the slides as well. Let me just go to that while we wait for this to run. This other example is also on mistakenness. And let me actually go back to my slides here. Getting started with 51, it's here. So, okay. We're going to be taking a look at this now. So here we're going to be able to find these digits, this weird O's that look like they have like a little head, or this nonsense that is supposedly an 8 in the ground truth of the MNIST dataset, or this spaghetti that is a 9 in the ground truth, or this crook 7, or these things that should have actually been labeled as unknown digit or ambiguous digit. These are things that should have been filtered out of the dataset instead of being forced into the taxonomy where they go into the 10 different classes. Something that is a very valid approach is that when you're doing classification and you have digits like this, you just have an extra class that corresponds to I don't know, because this avoids having the model being overconfident on things that it shouldn't classify as a 0 or a 7 or a 9. Like, that's something that is unnecessary. So here I'm gonna ask you a trick question, like which of these two models, this is like some output of the notebook that we're gonna see where we do the evaluation using 51. We're gonna be using clip that was evaluated and trained on a huge collection of images, 400 million image text pairs. And here we have it compared against a LeNet that was only trained on the MNIST dataset. Turns out that CLIP, even though it's an amazing general purpose model, is actually quite useless at MNIST. It's not able to distinguish between a 4 and a 9. And that's something that you see in the confusion matrix over here. You're also going to be able to see it in the notebook that I'll show you right away. Whereas the LeNet model that has been specifically fine-tuned for this is almost perfect. And it's able to do this with very little data and with a very limited amount of epochs in training. Sometimes you will find influencers in LinkedIn telling you that vision transformers have made convolutional networks obsolete. Well, that's not true. When you have a little amount of data, convolutional networks are the best thing that you can try. So here we have this comparison between a vision transformer, which is what you have on the left, is a clip vision transformer, versus a very small convolutional network that has been fine-tuned for this task. And the fine-tuned model is almost perfect, whereas the vision transformer that has millions of parameters and has been trained on the humongous amount of data from the whole internet is not able to distinguish between a 4 and a 9, simply because it's a very different domain than the images that it saw during its training. This is reported on the CLIP paper, and you can check it out. This is a domain adaptation problem that has become very trendy in the community in the last years. So we're going to be doing now a training loop in which we're going to be using the 51 dataset integrated with PyTorch in order to create a very, very good classifier for MNIST. We're going to be training LeNet to create a very high quality classifier. And I made another mistake here, which was to forget to put the link to the notebook in this particular slide, but I'm gonna give it to you right now. So we're gonna have this here, image classification and dataset curation with FiftyOne and PyTorch. So this is something that I'm also preparing for the FiftyOne tutorials. I hope that you find this useful. Let me put this into the notebook as well. Well, I think it is already in the repository. I think I put this into the repository here. I have this on getting started with image classification, the name. Image classification, yeah, this one. Yeah, I uploaded this 2 hours ago. And here you're gonna have like this weird message saying invalid notebook. Don't pay attention to it. It's just that some widgets in Colab do not work in GitHub. So you're gonna be able to open this notebook right away. If you just write here to Colab, GitHub to Colab. Let me just give you the link to this. Just press enter here. And this gives you access to the notebook. Here you will need to have a GPU. One reason why we're doing this in Colab and not in my local computer or your local computer, if you don't have a GPU, is that you will need a GPU to train the model quickly. So let me actually go to the version where I have a beefy GPU. I have here an A100 already attached. And we're going to be running this. It's going to run all and see what interesting things we get out of this notebook. It's very long, and it also covers concepts of data augmentation. So let me do some cheating over here and start while we're waiting for this thing to run. I'm also gonna give you the link to this on my slides. I'm gonna do here, link. Here you have my notebook. And let's see. So again, we're gonna have to install FiftyOne and the plugins and everything, because whenever you create a new Google Colab instance, everything needs to get reinstalled. You're basically getting a new computer. And this thing connect to the runtime? No, it didn't give me the A100 before, so I'm gonna have to run everything again. By the way, the thing that we did before with the duplication, there is a plugin for the duplication that you can use to basically do everything that I did through code in the FiftyOne app. And I included that at the end of the notebook. You can check it out. I also put a link to the tutorial where Jacob Marks was explaining how this thing works. It's a very nice plugin, and you can try and see how it works on the FiftyOne app. Let me actually try to show you this while we wait for this thing to run. I'm gonna go into this first part of a notebook. I'm gonna go again into this first notebook. I'm gonna go into this one, Dataset Deduplication. So what I'm gonna do is that I'm gonna run here just this thing from the scratch. And I'm gonna run at the end the output of the plugin for the duplication. This is way easier to use, but I recommend that you still check out the code. I still recommend that you check out the notebook that I have, because then you get a better understanding about what's happening with the deduplication plugin. The deduplication plugin is very nice for power users. I think it's better for you, if you're learning about the duplication, to read the code first. So what I'm gonna do here is I'm gonna do here session. Let me just do this here. And I forgot also to explain to you the file hash. Let me explain this quickly. So let me show you this. When you have this sorting by file hash, the cryptographic hash is unique for every image. So if I change just one bit of information in an image, the cryptographic hash is completely different. So if I were to scroll down and sort by file hash, I'm gonna be able to find the images that have exact matching hashes. So these two are exactly the same image. You see that they have the same size in bytes. And the FiftyOne plugin that we have from Jacob is able to find these exact duplicates as well. So if I go here, find exact duplicates, and going to execute, it's going to tell me that we have 9 exact duplicates. And I can also see this right away. I can go here into browse operations, and then I can make this appear again, display exact duplicates. I'm going to execute, and here we see the images that are exact duplicates and that should be removed from the dataset. And you see here that we have this full pipeline over here of selections. If I want to reset this, I can just click X here, and then I get again the full view of my dataset. This is something very convenient, these stages that we use for filtering the data in FiftyOne. So let me continue my chaos for today with my Google Colab notebook. Let's see. We have this saying that it's failing, so I'm going to save the changes. And let's see what's happening here. Amazing, because Colab is not connecting right now. What I'm going to do is I'm going to refresh this. And what I'm going to do is I'm going to change the runtime. So it's a cheaper GPU. The A100 is actually really hard to get from Colab. This is a very nice and beefy GPU. The T4 is a smaller GPU that it's good enough for what we want to do. I'm gonna say that I want it with high RAM. Here in too many sessions, I say that I wanna terminate other sessions so that they let me run this thing. And let's run this and see what we get out of this. See that Harpreet has gotten all the questions answered. Thank you. So let's see. Let's see if we get lucky with the GPU on Colab. It's executing. I included the plugin to evaluate classification performance. We usually have workshops on plugins. This is gonna come again most likely next month. We do them at least once per month, where we discuss how to build plugins and the variety of plugins that we have for this. Harpreet has built an amazing amount of it's just a huge chunk of functionality that we can put into FiftyOne, and the community is very active on this. This is a way that you can extend the functionality of FiftyOne without having to change the core framework. Many valuable things in FiftyOne you get out of the plugins that the community has built. So here again, we have like some discussion about clip. Here we discuss this image from the clip paper where we see the datasets where this thing doesn't work well. It's not good for MNIST, which is the dataset that we're going to be trying now. It's also not good for tumor classification in Patch Chameleon. It's not that good in satellite imaging from Eurosat, which I find a bit surprising because I have found it very competent on the images from Google Earth. And it's also not good at counting things. If you are curious about why sometimes humans in images generated by ChatGPT have 7 fingers, it's because CLIP is used to prompt ChatGPT, or at least that was till DALL-E 3. I think the model that OpenAI is using right now is probably not using the version of CLIP that they were using before. They probably have fixed this with more high quality data. So here we have, again, the visualization of the metadata, the height, the width, the type of the images, and the size in bytes. Here we have 51 being alive, but we'll have to close this because we're not working with that anymore. I want to take a look at my classifications here. So let me just pin this here and see where are we in execution right now. Right now it's doing the UMA visualization of the clip embeddings, which are gonna look surprisingly decent. Let's see, what do we get out of this last state of the app? So here we have a selection of 7s. For some reason I was querying that, maybe from the Similarity index. And here we have the images in the ground truth. This model, we haven't evaluated clip yet at this point because it's not attached here in the labels. We only have the ground truth. Again, we can take a look at the data here, and we can get some interesting stats out of this, like what's the ground truth distribution of the labels. You see that we have a mostly balanced data set with a slight dominance of ones. We have a count of 1,135 ones versus, oh, now it updated because we got the clip zero shot classification and I had a refresh over there. So this thing is still running. I ran the whole notebook. That's why we're getting like some updates during execution. Now it's downloading the train set from the 51 dataset soup. Before we're only evaluating this on the test set. And here I'm obtaining the training data because I want to get the performance of the model, of this LeNet model that I'm building in PyTorch. I want to see how good is gonna be my LeNet versus the clip model that we have evaluated a bit here before. This is what I show you on the slides. You see that the clip model is actually very bad at classifying digits. It's not able to classify the 9s from the 4s and things like this. Here's the classification report. And you see that the F1 score is very low. The accuracy is terrible, which is quite surprising because this is a huge model. Like in comparison with what you have with the LeNet, it's very surprising that this model does so bad on these particular images. But this is the nice thing about 51. We can be skeptical about every model. We can be skeptical about the data, and we can see how one thing influences the other. If I were to try to curate the dataset with CLIP, it will not be a good choice simply because the model doesn't have good performance on the classification of any of these digits. And if I were to only take a look at the embeddings, I might be a bit misguided because here, let me show you how the embeddings from Clip look like. They actually look surprisingly good. They look very good compared to the performance of the classifier. And that's something that might be misleading. So we need to consider everything holistically. We need to consider the performance of the model alongside the embeddings, alongside the algorithms that we're using to produce the embeddings, because different neural networks are going to produce embeddings differently. We're also going to need to be aware of the dimensionality reduction technique that we're using. So for example, here, let me show you, I have here embeddings produced by two different methods. Here I have the PCA embedding of the dataset. Essentially say that we want to visualize this by the ground truth label. PCA visualization. It's actually, let's see what's happening here. Let's get rid of this filtering here. And now we have all of the images in the ground truth visualized through PCA and the embeddings of clip. And you can see that we have some very nice embeddings over here. Like, I think these are the ones. These are relatively easy to pick. The clip embedding is good here. Here we have some 7s, some 4s. Here we have the section over here, which has some combination of 2s, 6, and 8s. PCA is a very fast algorithm for doing dimensionality reduction, but usually UMAP gives more interpretable results. Check it out. Let's do the comparison here. Let's filter this out. Let's get this here. And let's color again by the ground truth label. So here we have more separation in the groups, in the projections that we have here. They look almost clustered. They look clustered already. Like if I were to run a clustering algorithm here, it seems that it would be able to converge quite quickly. But this doesn't mean that this representation is good. So that's why I was saying that this is a bit misleading. We need to evaluate this holistically alongside the performance of the model. I put here a model evaluation. Here we have the LeNet evaluation and also the clip zero-shot evaluation. So here we can see that the data set, this was the same information that we saw in the notebook. We see that the F1 score is quite low. It has very poor precision, very poor recall, and even lower than the one that is reported on the OpenAI paper. In the OpenAI paper, they reported 88% accuracy, 88% accuracy, but they use a larger version of the clip model. They use one that had even more weights than this one. This is the base model. This is a relatively small model. Now we're getting here the mistakenness and hardness. The notebook is finishing running. So here we have also these metrics that tells how good is this data set in terms of the labeling. So for example, let's say that I want to get the full data set. I don't know, these are like some 90 samples of crappy images. You can see that these images are like very weird. These were things that I selected by hand, actually by sorting through the mistakenness in descending order. You can check it out. This is how I found this particular set of samples. You see that here we have like this weird thing that is supposed to be a 1, but the model believes that it's most likely a 6, and I would just delete this sample. This is something that is neither a 1 or a 6. It looks more like a C or something else. Here we have like this weird crooked 9 that I would also delete from the dataset, or I would put into a classifier that would put this into the I don't know label. Here we have like this 7 that is awful. It looks like the crossing between a 7 and a 1. And it's crazy, right? Because this data set is something that we all use to learn machine learning, and it's full of this nonsense. Like, how is this supposed to be a 9? How is this a spaghetti thing supposed to be a 9? We can do better by simply cleaning the dataset. If you go to Kaggle, I actually included some links in the notebook where there are some discussions about how to achieve perfect accuracy on MNIST. And the only way to achieve perfect accuracy having this crappy data is by cheating. Is that you put all the images that you have in your test set in the training set. That is something that you should never do. And that's the thing that we need to change as a community. Like we need to agree that we cannot out-train bad data, that we cannot out-model bad data because it's just bad. It's just sabotaging the performance of the model in the long run. So I encourage you to explore my notebook, and I think we're on time. So we're gonna have more workshops for 51 Enterprise and plugins. I encourage you to check out the list of available plugins. You can also learn how to create your own. Harpreet does some amazing workshops about this. And we have soon a verified auto-labeling event for 51 Enterprise, where there will be a large focus on data quality. You're going to see how these foundation models can be used to improve the quality of our datasets and reduce the labeling effort that we need to put into creating high quality data. So here, sorry for the bumpy ride, but I forgot to delete this as well. I invite you to please join our community if you're curious about what we're doing. We have a very active community that does a lot of events, and we have a lot of discussions through Discord. If you are curious about 51 Enterprise and the verified auto labeling feature, I would encourage you to book a demo and try it. Try 51. Pip install 51 is free, and you can use this with your own dataset. The data doesn't go to us in any way. And keep an eye for the events that we're going to be doing in the next weeks.